welcome to this problem walkthrough. Today, we'll tackle LeetCode number 34, find first and last position of element in sorted array. This is a popular problem that tests your understanding of binary search and array traversal techniques. Let's dive in and explore the problem and its solutions step by step. In this problem, we are tasked with finding the starting and ending positions of a given target value in a sorted integer array called nums. The array is sorted in non-decreasing order, which means the values either stay the same or increase as we move through the array. If the target value is not present in the array, we need to return -1, -1. The challenge is to design an algorithm that accomplishes this with a time complexity of O log n, which suggests that we need to use an efficient approach like binary search rather than a simple linear scan. The input consists of the sorted array nums and the target integer, and the output is a list of two integers, the indices of the first and last occurrences of the target, or -1, -1 if the target is missing. Let's look at an example. Suppose the input array is nums equals 5, 7, 7, 8, 8, 10, and the target value is 8. In this case, the first occurrence of 8 in the array is at index 3, and the last occurrence is at index 4. So, the output is 3, 4. This result tells us the range of indices where the target appears in the array. Now, consider another input where the array is the same, but the target is 6. Here, since the value 6 does not appear in the array, the output must be -1, -1, to indicate that the target is absent. Another example highlights the scenario where the input array is empty. If nums equals, and the target is 0, there are no elements to search, so the output is -1, -1. This demonstrates that when the array has no elements, we should immediately return -1, -1, regardless of the target value. These examples emphasize the importance of handling both cases where the target is present and where it is absent, including special cases like an empty array. To solve the problem effectively, we need to consider the constraints and edge cases. The length of the array, nums, can be as large as 100,000, and the values in the array and the target can range from -10⁻9 to 10⁻9. Since the array is guaranteed to be sorted, we can leverage this property to optimize our solution. Edge cases include situations like an empty array, a single element array where the target may or may not match, and cases where the target appears at the very beginning or end of the array. In all these scenarios, the algorithm must handle the inputs correctly and return the desired output efficiently. To solve this problem, there are two main approaches to consider. The first is the brute force approach. Here, we simply iterate over the entire array to manually find both the first and last occurrences of the target. We begin from the start of the array to locate the first index where the value matches the target, and then continue scanning to find the last such index. While this method is straightforward and easy to implement, it comes with a significant drawback: it's not efficient for large arrays. The time complexity is O(n), because, in the worst case, we may need to inspect every single element. However, on the bright side, it has a space complexity of O(1), as no extra memory is required. The trade-offs are clear: it's simple but not scalable, especially if the array is large or the target is absent. Now, there's a better way to tackle this problem by leveraging the fact that the array is sorted. Using binary search, we can optimize the solution significantly. Instead of scanning the entire array, we perform two separate binary searches, one to find the first occurrence and another to find the last. By doing this, we can narrow down the search space efficiently and avoid unnecessary iterations. Let's explore how binary search can be applied in this context. With the binary search approach, we perform two distinct searches, one for the first occurrence of the target and one for the last. To implement this, we define a helper function, findBound, which takes a Boolean parameter isFirst to determine whether we're searching for the first or last position. During the binary search, we adjust the left and right pointers based on the comparison between the middle element, nums, mid, and the target value. For the first occurrence, we continue searching the left half of the array if nums, mid, is greater than or equal to the target. For the last occurrence, we search the right half if nums, mid, is less than or equal to the target. This process ensures that we pinpoint the exact boundaries of the target's positions in the array. If the target is not found, we simply return -1, -1. The efficiency of this approach is a significant advantage. Its time complexity is O log n, because the search space is halved with each iteration, and its space complexity remains O1, since no additional storage is required. While it's slightly more complex to implement than the brute force method, the binary search approach is highly efficient for large datasets, making it a much better choice overall. In addition to the brute force and binary search methods, there are alternative strategies worth considering. One such alternative is the use of Python's bisect module. This built-in functionality allows us to locate the first and last occurrences of the target efficiently. However, while convenient, it may introduce some overhead compared to a customized binary search solution. Another option is leveraging a hash map. Here, we construct a dictionary that maps each number in the array to its indices. Once the hash map is built, retrieving the first and last indices of the target is a constant time operation, O1. However, the hash map itself requires O(n) time to construct an additional memory, which adds to the overall space complexity. These alternatives can be useful in certain scenarios, but they come with trade-offs. The hash map approach, for example, uses extra space, while built-in functions may lack the fine-tuned efficiency of direct binary search. Ultimately, while these methods are viable, they may not provide the best balance of performance and simplicity for this specific problem. After evaluating the different strategies, we choose the binary search approach as the optimal solution for this problem. Its logarithmic time complexity ensures that it can handle large datasets efficiently, and it takes full advantage of the array's sorted property. While the brute force method is easier to implement, its O(n) time complexity makes it unsuitable for larger inputs. Similarly, alternatives like hash maps or built-in functions either require additional memory or introduce unnecessary computational overhead. The key insight, or aha moment, lies in recognizing that the problem can be divided into two independent binary searches, one for the first occurrence and the other for the last. This separation simplifies the logic while ensuring correctness and efficiency. By iteratively narrowing down the search space, we eliminate irrelevant portions of the array, which is a major advantage over brute force. In conclusion, the binary search approach strikes the perfect balance between simplicity and performance, making it the most effective method for solving this problem. To start, the problem requires us to find the starting and ending positions of a target value within a sorted array. If the target is not present, we need to return -1, -1. Let's consider the brute force approach to solve this. First, we initialize two variables, start and end, both set to -1. These will store the indices of the first and last occurrences of the target value. This initialization ensures that if the target is not found, our result will automatically be the required default value of -1, -1. Next, we iterate through the array using a loop. For each element, we perform two condition checks. The first checks if the current element equals the target and if start is still -1. If both conditions are true, we assign the current index to start, ensuring we capture the first occurrence of the target. The second condition checks if the current element equals the target, and if so, we update end to the current index. This way, end is always updated to reflect the most recent occurrence of the target. After the loop, we handle an edge case. If start remains -1, it means the target is not in the array, so we return -1, -1. Otherwise, we return the values of start and end as the final result. Now, let's discuss why this brute force approach works. Since the array is sorted, all occurrences of the target value appear consecutively. This guarantees that a single pass through the array is sufficient to find both the first and last positions. Important edge cases are already accounted for. For an empty array, the loop doesn't run, so we return -1, -1. If the target isn't in the array, start remains -1, and again we return -1, -1. If all elements in the array are the target, the loop correctly identifies the first and last indices. In terms of data structures, the approach is simple. We use no additional structures, relying solely on the input array. The space complexity is O(1), as we only use two variables, start and end, to track the indices. Finally, while the brute force approach is straightforward and has a time complexity of O(n), due to the single traversal, we can achieve better performance using binary search. Since the array is sorted, binary search allows us to directly find the first and last occurrences of the target without inspecting every element. This reduces the time complexity to O log n. In terms of space, both approaches are efficient, with a space complexity of O(1), because no additional memory is required. By optimizing the algorithm, we achieve a faster and more scalable solution, especially for large input arrays. This implementation solves LeetCode problem number 34, find first and last position of element in sorted array. The solution uses a binary search algorithm to find the first and last occurrence of the target element in a sorted array. Here's the detailed explanation. The search range method defines a nested helper function, findBound, which performs a binary search. The isFirst parameter determines whether to search for the first occurrence, true, or the last occurrence, false, of the target. The findBound function initializes two pointers, left and right, to the beginning and end of the array. Using a while loop, it calculates the middle index mid. If the value at mid matches the target, the function determines whether it is the desired boundary. For the first occurrence, it checks if mid is the leftmost index or if the preceding value is less than the target. Similarly, for the last occurrence, it checks if mid is the rightmost index or if the following value is greater than the target. If these conditions are satisfied, it returns mid. Otherwise, it adjusts the search range by updating right or left based on the target's position relative to num's mid. The main method calls findBound twice, once to find the starting position, start, and again to find the ending position, end. If the target is not found, start ==-1, the method immediately returns -1 -1. Otherwise, it returns the range, start, end. This approach ensures an efficient solution with a time complexity of O log n, as it uses binary search to locate the target bounds. The algorithm handles edge cases, such as when the array is empty or the target is not present, by returning -1 -1. The implementation is concise, robust, and leverages the properties of a sorted array for optimal performance. Here, we start by defining our Java class and the main function, searchRange, which takes an array of integers, nums, and a target value to locate. The goal is to find the first and last positions of the target in the sorted array. Inside this function, we define a helper method called findBound that will be used to determine either the first or the last occurrence of the target. The method takes a Boolean parameter, isFirst, to specify whether we're searching for the first occurrence or the last. Now, we initialize two pointers, left and right, representing the boundaries of our search space, and then enter a while loop that continues as long as left is less than or equal to right. Within the loop, we calculate the middle index, mid, to divide the array into two halves. If the value at mid matches the target, we need to determine if it's the boundary we're looking for. For the first occurrence, we check if mid is at the leftmost position or if the previous element is smaller than the target. If either condition is true, we've found the first occurrence and return the index. Otherwise, we adjust the right pointer to narrow our search. Similarly, for the last occurrence, we check if mid is at the rightmost position or if the next element is greater than the target. If so, we return mid, otherwise, we move the left pointer to continue searching. If the target value doesn't match, we simply adjust our pointers based on whether the middle element is smaller or larger than the target. If the loop exits without finding the target, the helper function returns -1, indicating that the boundary doesn't exist. Now, back in the searchRange method, we use the findBound function to locate the first occurrence of the target by passing true as the argument. If the result is -1, it means the target is not present in the array, so we return -1 -1 as the output. Otherwise, we proceed to find the last occurrence by calling findBound with false. Finally, we return an array containing the start and end indices that represent the first and last positions of the target in the array. This approach ensures that we efficiently locate both boundaries using binary search, resulting in an optimal time complexity of O log n. Here, we're starting with an example where the array is 5 7 7 8 8 10, and the target is 8. First, we initialize the findBound function to locate the start position of the target, setting isFirst to true. The initial bounds of our binary search are left equals 0 and right equals 5, covering the entire array. Calculating the middle index gives mid equals 2, where nums 2 equals 7. Since 7 is less than the target, we narrow the search to the right half by updating left to mid +1, which is 3. Next, we recalculate mid is 4, and now nums 4 equals 8, matching the target. To confirm it's the first occurrence, we check nums 3, which is also 8. This means we need to continue narrowing the range by updating right to mid 1, making it 3. Finally, recalculating mid as 3 gives nums 3 equals 8, which matches the target and is the first occurrence since nums 2 is less than the target. We return start equals 3 as the starting index of the target. Now, we initialize the findBound function again, this time to find the end position of the target by setting isFirst to false. The initial bounds remain left equals 0 and right equals 5. Calculating mid gives us 2, where nums 2 equals 7. Since 7 is less than the target, we move the search to the right half by updating left to mid plus 1, which is 3. Recalculating mid as 4 gives nums 4 equals 8, which matches the target. To check if it's the last occurrence, we look at nums 5 equals 10. Since 10 is greater than the target, it confirms that nums 4 is the last occurrence. We return end equals 4. Combining the results for start and end positions, we have 3, 4 as the range where the target appears in the array. In the second example, we use the same array 5, 7, 7, 8, 8, 10, but this time the target is 6. To find the start position, we initialize the findBound function with isFirst equals true, setting left equals 0 and right equals 5. Calculating mid gives 2, where nums 2 equals 7. Since 7 is greater than the target, we narrow the search to the left half by updating right to mid 1, which is 1. Recalculating mid as 0 gives nums 0 equals 5. Since 5 is less than the target, we now move to the right half by updating left to mid plus 1, which is 1. Finally, recalculating mid as 1 gives nums 1 equals 7, which is greater than the target. At this point, left right 1 greater than 0, so we exit the loop and return start equals -1. Since the start position is -1, indicating the target doesn't exist in the array, the result is -1 -1 for the range. In the third example, the array is 1 1 1 1 1 and the target is 1. First, we find the start position by initializing findBound with isFirst equals true, setting left equals 0 and right equals 4. Calculating mid gives 2, where nums 2 equals 1, matching the target. To check if it's the first occurrence, we look at nums 1, which is also 1. This means we need to narrow the range by updating right to mid 1, which is 1. Recalculating mid as 0 gives nums 0 equals 1, also matching the target. Since there's no preceding element, we confirm it's the first occurrence and return start equals 0. Now, we proceed to find the end position by reinitializing findBound with isFirst equals false. With left equals 0 and right equals 4, calculating mid gives 2, where nums 2 equals 1. Checking if it's the last occurrence, we look at nums 3, which is also 1. This prompts us to update left to mid plus 1, making it 3. To continue narrowing down the end position, we recalculate mid as 3, where nums 3 equals 1, still matching the target. Checking if it's the last occurrence, we look at nums 4, which is also 1. Since it's not greater than the target, we update left to mid plus 1, which is 4. Finally, recalculating mid as 4 gives nums 4 equals 1, matching the target and confirming it's the last occurrence, as there's no subsequent element. We return end equals 4. Combining the results, the range where the target appears in the array is 0, 4. The solution employs a binary search approach to locate the first and last positions of the target element in a sorted array. Let's break down the time complexity. First, when finding the first occurrence of the target using the findBound true function, the binary search algorithm repeatedly halves the search space. For an array of size n, this process takes approximately log n iterations. Each iteration involves a constant number of operations, such as comparisons and pointer updates, which are O(1). Therefore, finding the first occurrence takes O log n time. Similarly, when locating the last occurrence using findBound false, the same binary search logic is applied, resulting in another O log n operation. Since these two searches are performed sequentially and independently, the total time complexity is O log n plus O log n, which simplifies to O log n. Now, let's examine the space complexity of the solution. The overall space complexity is O(1), meaning it requires constant space regardless of the input size. This is because the algorithm does not rely on any additional data structures like arrays, maps, or lists to store intermediate results. Instead, it uses in-place computations with a few variables, such as left, right, and mid. Additionally, the findBound function is implemented iteratively, avoiding the need for recursive calls, which would have required extra stack space. Consequently, the memory usage remains constant, and the space complexity is 1. Let's compare this optimized approach with a brute force solution. A naive method would involve iterating through the entire array to find the first and last positions of the target. In the worst case, this approach would require n time, as it scans each element in the array. However, the space complexity would still be 1, since no additional memory is used beyond a few variables. On the other hand, the binary search approach optimizes the time complexity by leveraging the sorted nature of the array, reducing it to O log n. This makes the binary search method significantly faster, especially for large input arrays, while maintaining the same constant space complexity. Let's analyze the best, average, and worst-case performance of this approach. In the best-case scenario, the target may be found at the very beginning or end of the array, allowing the binary search to terminate early. However, since the search space is still halved in each step, the time complexity remains O log n. On average, the binary search will also take O log n time as it consistently reduces the search space by half until the target is found. In the worst case, the algorithm performs the maximum number of iterations, which is proportional to log n, either to locate the target's boundaries or to determine that the target is not present in the array. Across all cases, the space complexity remains 1, as it does not depend on the size of the input. Finally, let's provide a mathematical justification for the big O analysis. For time complexity, each iteration of the binary search halves the search space, resulting in at most log n iterations for an array of size n. During each iteration, the operations performed, such as comparisons and pointer updates, are constant time operations, or O1. This leads to a total time complexity of O log n for each binary search. As for space complexity, the algorithm uses a fixed number of variables, such as left, right, and mid, which do not depend on the size of the input array. Since no additional memory is dynamically allocated, the space complexity remains 1. When solving this problem, there are several common mistakes to watch out for. First, not accounting for edge cases like empty arrays or arrays with only one element is a frequent error. For example, if you assume the array will always contain the target, you risk running into out-of-bound errors or returning incorrect results. To address this, make sure to explicitly check for these scenarios before proceeding with your main logic. Another mistake is relying on linear search for sorted arrays. While linear search might feel straightforward, it leads to O n time complexity, which is inefficient compared to the O log n offered by binary search. Leveraging the sorted nature of the array is key here. Additionally, confusion often arises with updating the low and high pointers during binary search. If these aren't managed correctly, you could end up with infinite loops or incorrect results. Testing and debugging your boundary conditions thoroughly is essential to avoid this issue. Another mistake to be mindful of is not validating the result after conducting a binary search. Just because binary search completes doesn't mean it has found the target. If the target isn't present in the array, you could end up returning invalid indices. To prevent this, always double-check that the target exists at the indices identified by your binary search. Also, overcomplicating the solution is a common pitfall. Sometimes, after finding the correct indices, redundant loops or additional checks are added unnecessarily. While these might seem helpful, they only serve to increase the time complexity of your solution. The key is to keep your implementation clean and focused, avoiding any computations that don't directly contribute to the final result. In an interview setting, there are specific insights that can help you stand out. First, be prepared to handle edge cases efficiently. Interviewers often test scenarios like an empty array, an array where all elements match the target, or arrays with duplicates. Demonstrating that you've considered these shows a thorough approach. Optimizing for sorted arrays is another critical point. If the array is sorted, binary search is typically expected. You should be ready to explain why you chose this method and how its time complexity improves the solution. Additionally, be prepared to discuss trade-offs. For instance, while linear search might be easier to implement, binary search is far more efficient. Make sure to clarify any assumptions, such as whether the array is guaranteed to be sorted, so you can choose the optimal approach. Lastly, practice solving variations of this problem, as interviewers might tweak the requirements to involve returning counts, ranges, or Boolean values instead of indices. This problem also connects to a range of related problems that can help you deepen your understanding of binary search. For instance, problem 34, finding the first and last position of an element in a sorted array, is the core problem for mastering binary search in this context. Problem 852, the peak index in a mountain array, introduces a unique twist to binary search by focusing on identifying a peak element. Another foundational problem is problem 704, which is a classic binary search task that helps you solidify the basics. Finally, problem 162, finding a peak element, extends binary search to scenarios involving local maxima. By practicing these problems, you'll gain a broader understanding of how binary search can be applied in various contexts. There are also alternative approaches to solving this problem, each with its own advantages and trade-offs. One option is linear search, where you manually traverse the array to find the first and last positions of the target. While this method is simple and easy to implement, it is inefficient, with an O(n) time complexity. A more efficient approach is the two-pass binary search. This involves running binary search twice, once to find the first occurrence of the target and then again to find the last occurrence. While this method achieves O log n time complexity, it does require careful handling of boundary conditions in both passes. Lastly, there's the one-pass optimized binary search, where you modify the binary search logic to find both occurrences in a single pass. This approach is faster but more complex to implement, as it requires managing multiple conditions within a single loop. Choosing the best approach depends on the problem requirements and your comfort with implementation complexity. Great job working through this problem. We explored how binary search helps efficiently solve array-based challenges. Remember, practicing problems like these sharpens your problem-solving skills for interviews and beyond. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!